will be this Saturday from 6 p.m. to 7:30 p.m. And unlike typical Saturdays, this Saturday we will have regular class where I will teach at some topic. So please attend without fail. Okay. So today's topic is analysis of algorithm and asymptotic notation. In the last class, we have um, seen the problem of finding minimum, maximum, second minimum, and so on. And we have seen a class of algorithms. We have compared how good is this algorithm, can we do better, or what is the sort of the best algorithm, or what is the minimum number of comparisons we need, so on and so forth. This all comes under analysis of algorithm. Whenever you have a problem, you have two jobs. The first task is the design of algorithm. That I'm not talking about today. That you have got a flavor in last class, and we'll be doing that throughout the class, throughout the course. The second step is analysis of algorithm. Now there is an in-between step. So first design of algorithm, and the second step is analysis of algorithm. The in-between step is extremely important, which is called correctness of algorithm. What is the definition of an algorithm? Algorithm is a sequence of easily executable tasks to solve a problem. So after you design an algorithm, and then you analyze its performance, how good or how bad it is, the important crucial middle step is that is it indeed an algorithm? Does it solve the problem? Is it correct? Does it work for all inputs? These are again extremely important question, and we will be pursuing this question throughout this course. But again, that is also not the topic of today's discussion. We are going at the third step, which is like analysis of algorithm. We have a problem, we have designed an algorithm, we have proved that this algorithm is correct. Now we are at a stage where we are studying the performance of the algorithm. So what is analysis of algorithm? It is study of goodness of the algorithm. Of an algorithm. Feel free to unmute and speak if you have any question, any doubt. All I need is your attention. This topic, this discussion, today's discussion in particular, is nothing non-trivial. It's very easy. All is needed is your attention. So if you do not understand any point, even if you are attentive, then it is like my fault that I am not able to explain or convey the idea. So feel free to unmute and just speak. I don't understand this. Okay, so this is the analysis of algorithm. It is the study of goodness of the algorithm. Now, what do you mean by goodness? Let's explore this. Let's expand this. By goodness, we mean that that is study of resource requirement of an algorithm. So it should take less resource. In some sense, that is good. What do we mean by good in this course? It means that it should take less resource. Now, what do we mean by resource? The resource can depend on context. So here are the possible resources. Most often, the resource that we want to minimize is time. Time taken to execute. from start of the algorithm till the end of the algorithm when the output is produced, how much time has been spent. That is the most important resource in most of the applications, and we will be focusing these resource most of the time throughout our course, throughout this course. And this is sort of will be our benchmark. We will typically say that algorithm 1 is better than algorithm 2 if algorithm 1 takes less time than algorithm 2. That is the typical thing. If we don't say elaborately or explicitly what do you mean by resource, then if nothing is said, that means an algorithm is faster. That means it is better. Can someone help me with some other resource? Please unmute and speak. And TS, please note down the name, whoever tells a good resource, name of a good resource.
Memory.
Sir, less memory requirement.
Memory.
Less memory. Yes, yes. Very good.
Space.
Space. Very good. Space needed. Anything else?
Lines of code.
Energy.
No, not lines of code. You see, we are an algorithm designer. Now we will deliver this algorithm, this software to a user. User does not need to know how much line of code is needed. All user cares is that how much time is required, or he or she needs to spend to get this job done. How much space it needs to give. So number of lines of
Less
code, it's
inputs.
not less. What?
Less inputs.
I don't understand. Less what?
Less inputs.
Less inputs. No. So whenever we are designing an algorithm, it's like the problem has been decided, input has been decided that this will be the input and this will be the output, like problem specification. So that's part of the definition of the problem.
Sir, number of test cases it executed.
No, that's also not users. That's also not the resource.
So less
Anything else?
less
Less,
processing power as possible.
less what? How much? What?
Processing power, like it should be least, or like what is possible.
No, what is an algorithm? Algorithm is a sequence of steps. Theoretically speaking, I can do that steps. I can do that step on a pen and paper also.
Okay.
So it's every algorithm is executable without computer with pen and paper also. It just need more time. So, but this is a very important point. This particular what we are saying is time. What do you mean by time? If I run the same algorithm on a older machine, it will take more time. The same algorithm, if I run on a faster machine, it will take less time. Does it mean that the same algorithm has become efficient now because I have a faster machine? Or the same algorithm which was invented 20 years ago was inefficient because we did not have a slower machine. We did not have a faster machine. No, that's not. And that indicates that we should clearly say what does time mean in this context, and that I'll come. But any other resource? These are your opportunities to get extra marks. Okay, I am helping. So these are all special kind of things depending on application. What it's depending on applications, these sort of resources can come up. Typically, time and space, these are always there for all applications. We want to minimize time, minimize space. But now the resources that I'm listing is sort of specialized to applications. For example, think of communication. We all have smartphone now. Now, what it is doing? It is any task that smartphone is doing. Most of the task, it talks with the server, so it needs a communication infrastructure, network communication infrastructure, wireless network to communicate. Now that's also a resource that requires bandwidth. I need to pay and recharge my mobile and get data connection. In this, due to pandemic, we know this very much. So an algorithm which requires much less communication overhead, much less bandwidth is of course a better algorithm. It is definitely a resource. I need to pay, and then I can get that resource. Like time and space is like invaluable. It's like it is always there. But for communication, it is definitely a resource. Can someone help me with another resource, which may be a critical thing for some application?
Maybe able to
Power.
power in the
Power, excellent, excellent. There are various operations which is all operations does not consume same power. Think of a mobile phone maybe 10 years ago. The batteries were not so powerful. Like so now to do the job to do the same job, if some algorithm consumes more wattage of power and another algorithm takes less power, depending on the application, say mobile phone, say RFID device, say a device on satellites, now they have limited power and optimizing power requirement is one of the design goals there. So power.
sir, can't power be linked to amount of processing power, like amount of processing it does?
No, not processing time. No, because you see, different operations can take different time. For example, if I tell you that do this addition, on the other hand, if I tell you that take a square root of this thing, it's extremely clear. It is clear to all of us that taking a square root is much more difficult task than adding two numbers. So if something is doing more thing or more heavy, power heavy constraint, for example, in an RFID device, a step could be sense this parameter and pressure right now and do this computation. Now to sense the parameter temperature, thermometer needs to be used. To sense the pressure, barometer needs to be used, so on and so forth. Now those all consume power. So if algorithm uses this power efficiently, it minimizes those operations which needs more power, then that is a better algorithm, depending on the algorithm, depending on the application at hand. Am I conveying the point? Can someone tell
Uh,
another resource which was discussed in last class? In last class, it was discussed. Another resource outside these four resources.
Sir, a different data structure.
That's the implementation. Think of user's perspective. Good. Who will say this is good or this is bad? User will say. Does user know? Do you know what data structure is used in the operating system or any software that you are using on your mobile phone? You don't care. All you care is about performance.
Cost.
Cost, but that's a very general thing. What do you mean by cost? So what I meant is comparisons. Last class we discussed tournaments. Now, and when we were discussing, suppose we have n players and how many matches we have to play to decide the winner. Now, although when writing the algorithm, we are doing a set x1, x2 to xn, and comparing is easy, just to greater than or less than comparison is done. But for many real world problems, any real world tournaments, this comparison is extremely costly. You have to conduct a match, and that amounts to a lot of money and huge burden. So you want to minimize the comparison in the tournament example. Am I conveying my point? So an algorithm for minimizing the number of comparisons is extremely important for designing tournaments. Say comparison between the ground set of elements x1 to xn. You can of course compare I with j and so on and so forth. That does not matter. Now, for that particular application, minimizing the number of comparisons may be more important than minimizing the time required for running the algorithm, space required, bandwidth means mobile communication requirement, power requirement, comparison. Minimizing the comparison is the ultimate goal there. Am I conveying my point? The main point that I want to convey is that
Palash,
don't be.
take the attendance if you have not taken.
Yes. Thank you. Yeah. Let me take that in. Please. Wait. Oh no. Okay. This is my iPad. Okay. So TS, please find out by Googling how to take attendance in MS Teams from iPad and unmute and tell me. Let me continue. Search in YouTube. You will see the video. Okay. So the
Excuse
main.
me, sir.
Yes.
Sir, but doesn't minimizing the number of comparisons indirectly mean minimizing the time complexity?
No, not at all. As I said, that there are various operations which will take more time than comparing the elements. For example, if these elements are just real number or natural number, then comparison is easy, and that is much faster than finding a square root. That is much faster than reading something from a remote desktop. Are you getting my point? But
Yes.
when comparison is like the underlying things are like real teams, and to compare, we need to play a match or something like that, then that is most valuable resource. The main point that I want to convey with all these things is that don't be blind and taken for granted that the only goal of algorithm design is to minimize time required, the execution time. No, depending on the application, it can be different other objectives also. The resources, the things that we want to minimize could be any other objective, and it could be others also. I can continue. I can give you another 5, 10 such examples, but that's not the point. I think you have got what I want to say. Okay, so now let's take an algorithm, a simple algorithm, and let's see what do we say or how do we analyze that algorithm.
Excuse me, sir.
Yes.
Sir, but then in this time taken to execute that thing, it also depends on the specific processor speed and the current processor load.
Exactly.
So then,
What do we mean by time? Let me define it. What
yes,
do you mean by time? Thank you. Very good. Time. So if the definition of time in this sense should be such. So whenever we are defining something, we first go back and see what are the needs, why we are defining it. It should tell us like on a same machine, on a same environment, if two algorithms are run under same conditions, like physics laws, if everything else remains constant, then algorithm 1, if it takes more time than algorithm 2, then, and if time is the resource that we are considering focusing, then algorithm 2 is better than algorithm 1. If everything else remains same, that means what? That means machine, that means the other processors, other applications that are running at that particular moment of the time at that machine, because you can have the same machine, but if you run that run a program when the machine is idle versus you run a program when the machine is very busy with doing hundreds of jobs, then it will take more time. So the definition of time should be like independent of these sort of things. So here is our definition of time. Time is number of basic steps. What do you mean by basic steps? Basic steps means, as I said, in the definition of the algorithm, we, in an intuitive level, we define, okay, these are the basic steps. What is the definition of an algorithm? It's a sequence of basic steps. If anyone performs those basic steps, then it solves the problem. Solves the problem means it will compute the output from the input given. Now, what do you mean by basic steps? That let's not go deep into it, because that will vary. But anything that say we can do it in a piece of pen and paper with small effort. It's not that in a pen and paper I will need one year to do that basic step. No. So like basic steps is like addition. You can add two numbers. Subtraction. So let me add this way. Arithmetic operations. Arithmetic operations. Like basic arithmetic operations. It does not mean that I need to solve a Diophantine equation, which no computer can solve. If you don't know Diophantine equation, forget about it. Then it's just go with our natural understanding. Basic arithmetic operations, the number of it, and what? And basic logical operations like comparison, whether two things are equal or not, logical operations. Actually, all a computer is capable of doing is arithmetic operations and logical operations, basic ones. If you read microprocessors, how they work, it hands out a list of basic arithmetic operations and a list of basic logical operations that it can do. That's it. Now, if you want to do any sophisticated application, you convert it. Computer hardware only understands this language. Tell me which arithmetic operations from my given list of arithmetic operations you want to do, and tell me what logical operation you can do from my list of operations. And there is some control operations, like you take these, like control operations, but that's minor. Yeah. So from computation perspective, only these two things that what a microprocessor computer at its core is capable of doing. So it does not matter how sophisticated application you are seeing or you want to write. You know that at the heart, all those sophisticated and high level things has to be converted in terms of these things. All the computations that you do has to be converted into basic arithmetic operations and basic logical operations, because the job has to be done by computer hardware at the end of the day, and computer hardware understands only this language. Now here also there is some unhappiness. Can someone give a criticism about, okay, time is not also the number of basic steps. Can someone criticize this step?
So could you repeat the
So
question?
usually the more complex steps take.
Yes, continue. The girl, continue, please.
Yes, sir. So like these
please.
basic do not cost a lot of time as compared to the complex operations, which actually contribute more to the time taken in the execution of the entire code. So maybe that's why.
Okay. 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 I don't think this is what I was meaning, but under basic operations also, the most basic operations that arithmetic operations that we teach to school kids, means LKG, UKG, is what? Addition, subtraction, multiplication, division. Now we all know that addition is much simpler than subtraction. Subtraction is much simpler than multiplication. Multiplication is much simpler than division. And it is true. The best algorithm known to add two numbers is faster, takes less time than the algorithm for subtraction. Then followed by the algorithm for multiplication. The best algorithm known, it takes more time. So how do you say, for example, if by your definition, if an algorithm does 100 additions versus an algorithm which does 99 divisions, the algorithm which does 99 divisions is better. That's not the case, even if that does not match our intuition of time. Are you getting my point? Among these basic operations also, there are some operations which takes less time, which takes more time. Now, by this definition, if we simply define by time, we mean that the number of basic steps. Then if an algorithm does 100 additions, and there is another algorithm which does say 99 divisions. Now divisions is much harder than addition, and hence it will definitely take more time. But by this definition, you are saying that no, the second one, which does 99 divisions, is better algorithm. Does everyone agree with what I am saying, or getting the criticism of this model? Yes.
Okay. That it should be proportional to cycles it takes.
Correct. Correct. Yes. Okay. Okay. So everyone have understood the criticism. Can someone give me the answer? What should we do?
Then instead of time, we should calculate time taken per operation.
So maybe we can ignore, because there are few problems which have such a clear distinction of doing 99 divisions and versus 100 additions. Mostly we do a combination of both, and they can more or less even themselves out.
Very good. This is the thing. Do nothing. Have peace. Let's see why. So what do you mean by do nothing? All I mean to say is that be satisfied at that granularity. Don't be so much in a rat race to distinguish between two algorithms which are anyway very close apart. For example, where I am writing this, I am writing in my iPad. Can someone say no, this is not an iPad? This is, if you look carefully, there are only atoms. These electrons are running around it, and so on and so forth. But that level of granularity is not useful in this context. And you will, at the end of the class, my job is done for today's class if you are convinced that the extreme example of 99 multiplication versus 100 addition, that level of granularity is neither needed nor possible. So we have to be satisfied with this level of details, this level of granularity. So the main point here is that by time we mean the number of basic steps. That's it. That's the final thing. And in the remaining time of the class, I will motivate you. I'll tell you, show you why it is enough to do that, and why we cannot go beyond. Okay. Let's take an example. Enough talking, enough theory. If I don't give an example, you will catch me. So let's take an example of a simple search problem. Very easy, and it takes an integer array a 1 to n. See the flexibility of pseudocode, because I'm not writing a C code or C++ code or Java code. I'm writing pseudocode. I can write A1 to n. If I was bound to write a C code, I could not write 1, comma, dot, 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 n. That's the flexibility. And because of pseudocode, we in algorithm design are able to focus on the exact method, not the details, not the implementation details of any particular language. Okay, so what this is a search subroutine I am writing. What it does, it has a simple task. It has an integer array of 1 to n, and I have given a key, and it will search in this array if it is there or not. If it is there, it will return the index. Otherwise, it will return -1, which is an invalid index. -1 invalid index means that it has not been found. Let me write for loop I equal to 1 to, again let me use the beauty of pseudocode. For I equal to 1 to n, I dot 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 n. What do I do? If AI, again beauty of pseudocode, I don't have to do double equal to. If AI equal to key, then return I. And if we are not able to return anything at the end of the for loop, that means we have not got the item, return -1. Okay. Now, again, let me again motivate. Why number of basic steps? Because first motivation, why we should be happy at that level of basic steps. First motivation, the number of basic steps. Which steps are basic steps? That depends on machine to machine, computer to computer. Even in today's computer, if you take various models of PC, then the basic instruction set is maybe different from processor to processor. The basic instruction set for an AMD processor is different for Intel processor. Forget what was the basic instruction set 20 years ago. So if you sort of dig too much into this basic, you'll be in trouble, because what are the basic steps, that is itself is changing from time to time, and that's not our focus. First point for being contained at the basic level. Second, we are writing an algorithm, and as I said, an algorithm is a sequence of basic steps. That algorithm can be executed in any machine. Even in the fast computer that was discovered, that was invented, and even today's computer, and another supercomputer which will be there after 50 years. The base same this piece of code can be written there. So what do you mean by this basic? So then we need to sort of generalize this basic. We need to somehow make this basic machine independent, because machine will keep changing with time. The basic operations that we define is like at the pseudocode level, for example, and just you can of course dig into it, but there is no need to dig into it. For example, what are the basic operations here? Initializing I equal to 1. Is it a basic operation? Yes. Then every time I have to increment I equal to I plus 1. Is it a basic operation? Yes. Then in the if I am checking AI equal to key or not. Is it a basic operation? Yes. Then I am returning I. Is it a basic operation? Yes. Just use your intuition. That's it. So we know all the basic operations. So for this, at least for this algorithm at the pseudocode level, let's all agree that we know what the basic operations we are all talking about. Then the second task is, now we need to count the number of basic operations, isn't it? Now we have all understood what do we mean by basic operation, But to compare one algorithm with another algorithm, I need to count what are the number of what is the total number of basic operations in algorithm 1, algorithm 2. So can you help me? What is the number of basic operations here? For example, for this for loop, let me use some other color. Which color shall I use? I think this color may be better. Is this color visible? If some color is difficult to see, you let me know.
Yes, sir.
For example, yes, okay. So for this for loop, just focus on this for loop. How many basic operations it will be needed? It will do.
So 3 for each iteration or 3n in total.
Correct. Like 3 per iteration, like 3 per iteration. This piece of code.
Sorry, sir. It should be 2 per iteration.
Okay, I am
because it's
writing
just
all
incrementing and
candidates.
comparing. I'm sorry.
No problem. I'm writing all candidates. 2, 3. Okay. Now, if how many times this comparison will be executed?
One time
Seems one, right?
for each
One
iteration.
per iterations. This particular thing, one.
One in total.
One in total. Total. One, always one, or 0 also can be there, right?
Yes, sir.
Yes, I'm extremely bad at these things. Now we have a golden opportunity to catch my mistakes. It will be a means you won't get a better opportunity to catch my mistakes than this. How many times this will be executed?
So this is also 1 or 0.
0 or 1, but it is also some way connected. So let me use something, just something, some way connected in how many times return will be. So 0 or 1 total. So can you tell me now when we are comparing two algorithms, we want to say that algorithm 1 takes this number of steps, algorithm 2 takes this many number of steps. Can you tell me how many steps this particular algorithm will take?
So total number of iterations plus 1.
Don't tell me those iterations. Don't be because you know what was our goal? Remember, what is the goal? Yes, yes. What was our goal? Initial motivation. Why we are analyzing algorithm? If for any problem there is only one algorithm possible, there is no need to analyze the algorithm. Because for one problem we can have tons of algorithms. We want to say that this algorithm, it's like quantify the goodness, that this algorithm is this much good, this algorithm is this much good, so that we can compare these algorithms. Now, so exactly how many basic operations an algorithm performs?
So 2 plus 3n.
Answer. Let me write. Can someone tell me the answer?
So 2 plus
It's
3.
3n plus 1.
n plus 1.
तुम्हारा
2n
मुंडू
plus 1.
तुम्हारा मुंडू
Sir, 1 plus 3n.
We can't tell exactly, sir.
How can I tell? Look at the poor girl or boy who was trying to tell like it will depend on the number of iterations and got a scolding from me. But you know, if you are asking, give me one number, that is not possible because it depends on the number of iterations. So, so because it depends on number of iterations. On where does the number of iterations depend? Why number of iterations vary? Because the input can vary. So in particular, the exactly
Yes.
how many basic operations an algorithm performs, that of course depends on input. If key is present in A1, then it is minimal operation, minimal number of steps it is required. If key is not present, then many more steps will be required. So now again, it is sort of, we are in a conflict from our goal. What was our goal, our initial motivation? We want to say that we want to compare two algorithms. Now, if performance does not come as a number, which is easy to compare, and it comes with so many qualifications. If input is this, then this is this. If input that, then this, then this, then this. Then, and for every two algorithms, we have this sort of huge description of performance. Then how will I compare? This is a tremendous job.
We
This
can
is a
compare
horrible
upper
job.
limit.
Sorry? Sorry,
So we can
someone was
compare upper limit of
compare what? Sorry?
upper limit means worst case
Yes,
in worst
yes,
case.
yes. That's what we were doing. That's what we are going towards. So what we do is that what we be content with is, we should be content with is not upper limit. Worst case number of comparisons is this upper limit. You are right. Number of steps. Let me not write basic all the times. Worst case. So among all possible inputs, you see that which one for what input it is taking maximum number of steps. Let's use that number only. Of course, if means we are making this simplification for both our need, because it is need, because it is otherwise it won't serve the purpose, and it is both it is our need and also it is so difficult. So we need to do either worst case or best case. Best case is minimum over what is the minimum number of basic steps it will execute, or average case. Like on an average, how much how many number of steps an algorithm is needed, algorithm will perform. Now among these three, which one should we use? These three are the first obvious candidates. Which one should we use?
Worst case,
Worst case. Why?
because if we are able to solve the worst case, for any case also we will be able to solve.
Okay, you have read the book. Okay, so let's eliminate which one we should not use. We should never use, or we should,
So
I
the
don't know,
best
it's best
Best
case.
Best
case.
case for
Very good.
everyone.
Best case is like, who want best case? My life is so difficult. No, nothing best happens in my life. Okay. So, but how about average case? It sounds pretty good. You know, there could be an algorithm which takes many steps for only one or two inputs, and for everything else it is pretty fast. For them, it is worst case is like horrible. Worst case is like calculating your SGPA based on not the average of your performances in individual subjects, but taking the worst performance of your subjects. Is this a good evaluation of your performance? What do you think? Average case or worst case? Which one is better evaluation of the performance? Say your SGPA.
Sir, average.
Average case. This is sort of obvious that average case is much better benchmark than worst case, because it takes all the things, all the inputs, and the performance of the algorithm across all inputs, and finds out, okay, in average, on an average it will take this much steps. Now give me a few reasons why I should not use average case and I use worst case. In this course, and mostly in algorithm design, 99% of the time, and almost always, the whenever we say how good or how many number of steps, we always mean worst case, not average case. Tell me why.
So
Give me few reasons.
So one reason which I can think of is that in the to calculate the average case, we would have to do a lot of computations.
Very good,
Best and worst.
excellent, excellent. Just look at this small tiny piece of code. Computing worst case is so easy. Computing average case is so difficult. Very good. Any other reason? Very good. And that is sort of the one of the main reasons that he has told. Any other reason?
So average case may miss out some of the extremities of the worst case.
Correct.
Like
but so what's the harm? You're on the right direction. What's the harm?
we will miss out on some useful data, and
but then worst case misses out more on useful data, no?
I mean, if we're able to solve the worst case, then average case we can also solve, right?
No, it's not like we are solving this algorithm analysis. We want to now know the number of basic steps because we want to know how good is this algorithm. We're not solving anything. Algorithm has been already designed. We have proved that it is a correct algorithm. Our job is to evaluate this algorithm. How good is this algorithm?
Yes. So
why on that parameter also, let me tell why worst case is better than average case. Okay, I'll leave you with this thought. You find out. But here also you see that okay, so the number of operations, let me write this way. So it was like less than equal to what was there? 4n, right? 4n plus 1 or something like that. Something like that. Now, you know, this is 4n plus 1. Now, I'm sure that if you look this carefully, and you know, you are not going to write a pseudocode. When you are writing real software, you will run this, you will implement this pseudocode in a real programming language, either C, C++, Java, Python, whatever it is. Now, depending on the implementation of the same pseudocode, the number of comparisons will change. Depending on whether you use for loop or while loop or do while loop or something else, the number of comparisons will change. So what is needed is that this exact numbers is not required, because these exact numbers, like whether it will be 4n plus 1 or 4n plus 2 or 4n plus 10, or will it be 4n or it will be 3n or 5n, this small constant does not matter much, because that depends on the implementation. Are you getting my point? So we will be looking at focusing on, like Arjuna, on the big picture, the main term. The main term here is n. Okay, the main term here is n, and that is formalized in this asymptotic behavior. Suppose we have two functions f and g. Our functions are from natural numbers to natural numbers. Natural number is, for me, it is 0, 1 to n. 0 has been infinity. 0 has been not infinity. Let me not write infinity. 0 has been invented in India. I want to include 0 in natural number. There are two communities who include 0, who does not include 0. Okay, I just include 0. So here is first most useful notation, big O notation. It is called big O notation. We say two functions, f and g. F is big O of g. That's how you read. If let me first show pictorially, but it is essential you know the definition. Pictures won't help. Suppose this is f and this is g. So f is big O of g means that, you know, initially for small values of n, there can be this f can take more value, g can take more value, and so on and so forth. But after some time, after some say n naught, beyond n naught, f means g always dominates f, like that. That is the spirit. And that's why this spirit is not enough. That's why we go to the exact definition. So we'll say f is big O of g if there exists a constant c greater than 0 and there exists a natural number n naught in n naught depends on c. That means you first choose c, then appropriately you choose n naught. It can be chosen based on what c you choose. There exists a c and there is a n naught such that f of n is less than equal to c times g of n for all natural number n greater than equal to n naught. That means focus on only large numbers. Forget these small spitty natural numbers who are there from 0 to n naught. Beyond n naught, f is dominated by g, and also allow some small constants. As I was explaining here, don't worry too much about whether it is 4n or 3n or 2n or 10n. Forget these small constants. Take a high level view. This big O of fn is big O of gn. There is another very popular big omega. The answer is just opposite. The spirit is just opposite. We say f is big omega of g if g is big O of f. And another popular one is theta. We say f is big theta of g if both f is big O of g and g is big O of f. If both holds, then we will say f is theta of g. For daily use, you can think of big O as like less than equal to f is big O of g. Basically, high level in spirit means that f is less than equal to g. Although it does not make sense, you can all immediately catch me, because these two are functions. We are comparing functions. We are not comparing numbers. We can't say that one function is less than other function. So because we can't say that, that's why this notation big O. But for all like intuitive level, but if you and I are friends and you don't catch my mistake, then I can tell you, basically f equal to big O of g means that f is less than equal to g between you and me. Similarly, if f is big omega of g means that f is greater than equal to g. Don't catch me, but that's basically it means. And f is big theta of g means that f is less than g. Sorry, f is equal to g. So these three are the main asymptotic notations that we will use throughout the course. And there are some properties, very standard properties, trivial or easy properties like this. If big O of f plus g is big O of f plus big O of g, something like that. Sort of properties. These are like trivial or easy properties. And why only big O? It also works for omega. These are in books, very easy to verify and prove. let me not spend much time. This is mechanical. Okay. Okay, so I've run out of time. That's it for today from now. From me, we will meet on Saturday, 6 p.m. We will have a regular class from 6 p.m. to 7:30 p.m. this Saturday. Please join there. If you have any other class, you can leave. I am here to take your questions.
Sir, for the worst case, we are getting the maximum time. So
Correct, but
that's
our we want this to compare two algorithms. Now, for both algorithms, we are getting maximum time, and you're right that it may be possible that one algorithm almost always does better most of the time than other algorithm, but that algorithm only in once or twice it takes so long time. Its worst case number of steps is much higher, and we are falsely concluding that algorithm 1 is worse than algorithm 2 because worst case time complexity, that is the term is used. Just get used to it. Time complexity means the number of steps. The time complexity of algorithm 1 is less than algorithm 2 because the worst case time complexity of algorithm 1 is less than worst case time complexity of algorithm 2. But in practice and in reality also, algorithm 2 is better because there is only one or two instances where algorithm 2 takes more time, but in almost all other instances it is much faster, much better than algorithm 1.
So we can actually use the mix of both, like for the worst cases.
The idea is that in the yes. So the more thing, if you can combine all, use all three, then even better. Each one gives one picture. It is like seeing an elephant from various things. Now, average case, it give an overall idea. Worst case is one perspective. Best case is also another perspective. So to base of course it will be better if you can evaluate if you can find out, or then if all the three for every algorithm, if we define that by performance we mean worst case time complexity, best case time complexity, as well as average case time complexity, these three numbers, then we run into a trouble that we don't know how to compare any two algorithms. And the answer is not very clear. It for example, the algorithm could be for a really critical job, like like it should not take this more than this much time, say, or for a sensing device in a safety application. After the execution of the algorithm, some alarm system or some very important task has to be initiated. Now there, the worst case is the benchmark. It does not matter whether I don't want average case. I want my algorithm to finish before this much time. So again, you see that now not only on the algorithm, not only on the problem, on the application also, it depends which one you will consider, which one you will give most priority. Worst case, best case, or average case. Think of an application of fire alarm system. Their worst case is the worst case guarantee I want. If a fire has broke out, it does not matter, for all possible circumstances, it should take the least amount of time. On the other hand, if there is an algorithm, I give you an algorithm for say fire alarm system, which almost always it will 99.99% of the input, it will give immediate within 1 second. But there can be some cases for which it will take 1 hour. Versus another algorithm which will always finish its job within 2 seconds. Which one is better?
So within 2 seconds.
Of course.
Okay.
Now I can give you the same algorithm, but another application where the first one is better. So what is needed is that you must understand these things. You must understand these benchmarks, what are its drawbacks, what are its use, so that in your job, in your future life, you can apply you can take the decision, analyze and take the decision which one is needed in the application you are doing the algorithm.
Okay, thank you.
And that's why I spent most of the time, if you observe closely, most of the time answering or motivating this message or conveying this message. It's not that one is better than other. You have to know what are the pitfalls, what are the drawbacks. And I spent least amount of time on this asymptotic behavior, which is very mechanical, very mathematical and mechanical, easy, which any one of you, all of you can just pick any book from our reference books and read these trivialities. But what I have seen most of you miss is that which one is better, worst case or best case or average case. It depends on so many things. Even if the problem, you fix the problem, fix the algorithm, depending on the application, worst case may be better than average case, or the other way also it can be the case. Anything else?
Sir, what does the alphabet C represent in the big O notation? Is it just an arbitrary constant?
Yes,
Or-
yes, there exists a constant C. This C?
Yes, sir, yes.
There exists a constant C. Constant. There exists, let me write specifically, constant.
Okay, sir.
This is also constant. N naught is also constant. C is allowed to be a real number, positive real number. N naught must be a natural number. All of you will be expert in doing big O, big omega, theta. And if you sort of be expert in the first 45 minutes of my lecture today, at the end of the course, then my task of teaching you algorithm is sort of almost done. Questions? Okay, so if there is no more question, so let's please join us at 6 p.m. this Saturday. Thank you.
Somebody should
Excuse
stop
me,
the
sir.
recording.
Yes, yes.
Um,
Yes.